Hello and welcome back to digital signal processing. In this video, I will show how to use fast Fourier transform function in MATLAB. I hope you all know what is fast Fourier transform. Let me explain. Fast Fourier transform converts signal into individual spectral components and provides frequency information about the signal. Now we'll use this function in the MATLAB. Before that, we have to take a signal because FFT converts the signal into individual spectral components and gives us the frequency information of the signal. Now I'll consider a signal here and let the signal be a sinusoidal signal. You all know what is a sinusoidal signal, how to represent a sinusoidal signal. So any sinusoidal signal is represented as A sine omega t. That is A sine omega is 2 pi f into t. So let us write A is the amplitude, right? Sine of omega, I told you we can write it as 2 pi f. 2 into pi is a constant value, f is a frequency, and t is the time. This is the sinusoidal signal. Now we have to assign the values. Amplitude I'll consider as 2, frequency as 8, and the time I'll consider 0 to 1 with an interval of 0.01, right? That is a time. So we have given the values, all the values in the formula. First, let us try to plot this subplot to 1, 1. So 2 plots I'm going to plot. So this is the first plot, subplot 2, 1, 1, plot t. With respect to t, we are plotting the signal x. So save the program and run. So this is the sinusoidal signal. So x-axis we have the time period, right? The 0 to 1 we have considered, and this is the sinusoidal signal we have considered for the program, right? Now we'll find the FFT. Now in MATLAB we have two functions, that is FFT can be calculated as, we can write FFT of x, or we can write as FFT of x comma n. I'll tell you the difference between two. First, we'll take what is FFT of x, and I'll show you how we get the output values when we use FFT of x, and then I'll explain about FFT of x comma n. So y is equal to, consider a variable y, use the function FFT of x. So it has to compute discrete Fourier transform of x having samples as same as x, right? So if you try to plot this subplot of 2, 1, 2, so second plot, I'm going to plot of y. Okay. So I have used FFT of x function. Okay. So FFT of x computes discrete Fourier transform of x, and the number of samples will be the same as the signal x. Now, I'll run the program, and if you see here the graph, why we got a graph like this is, if we check the values of y over here. So if you see this, if you find FFT of x, if you use that function, it gives complex values. So complex value is a value which has a real and imaginary term, right? You can see here we have real value and the imaginary value. And we are trying to plot the y value, both with the real part and imaginary part. That's why we got graph like that. Now, instead of that, we can use absolute value of the function. If we use absolute value of this, I hope you all know what is called absolute value. Absolute value of FFT of x. So run. Now we can see the spectrum, right? So it converts the time domain to frequency domain. Now you check the output values, so it has only the absolute values of the function, right? So that is the importance of using absolute. And here, if you see the spectrum also, we have the spec. So run this program. So run this program and see we got the spectrum and other components of a spectrum are not visible. But that what we have to do is we have to use the function called FFT of x comma n. Now what is this n? FFT of x comma n. It returns n point DFT. And the value of n must be integral power of 2, right? The advantage of using n is that as n increases, resolution in the frequency domain will be increasing. And if we are using this function f of t of x comma n, as I told you, n must be integral power of 2. And if we compute here, and also we have to keep it in your mind that the number of samples of FFT always should be greater than number of samples of the original signal. So you have to choose n value properly. So it is an integral power of 2. I'll choose 1024. So this is another function FFT x comma n. So run this. Now we can see the component, right? Individual spectral components, and we have chosen n value as 102. As I told you, that FFT converts signal into individual spectral components. So we have the individual spectral components, and it is giving the information regarding the frequency of the signal, right? So it is a double-sided spectrum. So this is the input signal X, and this is your FFT signal, right? FFT of the X. So I like again explain the program. I have taken a sinusoidal signal A sine omega t, where A is the amplitude. Omega, I have expressed it as 2 pi f. F is the frequency, T is the time. And I have chosen some values for amplitude, frequency, and time. I have chosen a time interval from 0 to 1 with an interval of 0.01. And then first I plotted x, the signal with respect to t, and we have seen the sinusoidal waveform. And after that, I have used the FFT function, that is in the MATLAB. So we have to, as I told you, we can write FFT of x, which converts the discrete Fourier transform of the signal, having samples as same as the signal x, whereas FFT of x comma n will return n point DFT. And we have to choose the value of n properly and in such a way as the n value increases, the resolution and the frequency domain will be increasing. And also the number of samples of FFT should be greater than or equal to number of samples of the original signal. Otherwise, we will not get a proper output. You can also see the output value because we have taken the absolute values. So FFT will give a complex number, but we have considered absolute value of FFT of x comma n. So it takes only the absolute values. So this is that I can see, check the input signal and the frequency spectrum, right? Double-sided frequency spectrum. So this is how we can use the FFT function in MATLAB, right? I hope you all understood how to use FFT function, why we have to choose absolute value, why we have to prefer absolute value of FFT of x, what is the importance of n value, in FFT. Thank you.